Hello, my name is John Ellis Guino-o. We will just continue on this last assessment too. On the previous assessment, the Sydney and Melbourne branches were already connected, and then the network was working, but the ABC company has reported that there's some delays in services and communication between these two branches, and also within the Melbourne virtual lands. So the company believed that the current routing and switching setup, together with the lack of network redundancy, could be contributing to these problems. So they also wanted to add wireless networking, improve network monitoring, and provide a point-to-point GRE VPN tunnel between the Sydney and Melbourne. So for this assessment, I made several improvements, as you can see here at the screen, and to address these requirements or these problems. So the first problem is the current RIP routing. In the last assessment, I used the RIP version 2. So our RIP work well, but it can just work in a small network or on a small company. But since ABC is now experiencing delays and wants the network that can handle future expansion and network changes, so that the network can be better at the future. So I have two options here. So OSPF and EIGRP. EIGRP is also a good option, but because it can quickly respond to network changes and uses information such as bandwidth and delay. However, OSPF is the best solution here, or the best option, because OSPF is a link state routing protocol and uses a cost to select the preferred route. So we can manipulate which route it can goes to. It depends on how much it costs. So it can also automatically find another available path when a link fails. So because of this, I replaced the RIP to OSPF here. So I already removed the OSPF current routes here so that I can demonstrate it properly. So here it is, and this one. So I will show you guys that the RP has already been replaced. So we'll go to this router here. So just here I am checking the routing protocol on the Sydney router. So we can see that the routing protocol is now OSPF process 1. So this confirms that the RP has been replaced with OSPF. So same with the this one, but yeah, I'll just show you guys the OSPF neighbors from the Melbourne router is 1.1.1 at the 0.0.0.1, and the router 2.2 yeah, this one at the 0.0/0. So both are showing at a full state, and this means that the OSPF neighbor relationships are working and the routers can exchange routing information. So I'll show you guys the normal routing or OSPF routing here. So just go for Sydney working. So during the normal operation, OSPF use the existing route through the core router, which is in here, and the trace route goes to the 4.4.4.2, which is the core, and then it goes to the 5.5.5.1, which is the Melbourne router here, and before it can reach the Melbourne IT computer at 192.50.0.10. So under the normal condition, the path is Sydney yeah, the path is Sydney, and then core, and then Melbourne. So that is the normal route. So since there's a problem with the lack of redundancy, I will show you guys the Sydney to Melbourne connection here. So this connection here. So the second problem is, yeah, the one redundancy. So in the old design, Sydney had only one path to Melbourne through our core, which is here and then here. There's no connection here. So this means that if Sydney to core connection fails, Sydney could lose communication to Melbourne. So there's no backup or anything. So just to solve this problem, I added a direct backup connection between the Sydney and Melbourne, which is here. So I already configured the higher OSPF cost on this connection so that it can be manipulated in case we don't want the connection goes through here normally. It just is, since this is just a backup one, so I added more costs on this connection. Will stays available as a backup route, and then yeah, so and now I will demonstrate what happens when the main connection fails. So here, so I have now disabled the primary Sydney to core connection. So after the connection goes down, OSPF automatically calculates the available route. So the routing table now shows that the Melbourne network is using the 6.6.6.2 here. The trace route shows that the first hop is 6.6.2 as well. And this is the direct backup connection between the Sydney and the Melbourne. This demonstrates that even if the primary one connection fails, the two branches can still communicate through the backup path. So I'll just restore this one. So I already restored the primary connection. So once the link becomes available again, OSPF can return to the preferred route through the core. The next problem is the wireless network security. So I already added here the access point for Sydney. So ABC wants to provide the wireless access in both branches, which is this one and then this one. Wireless networks can be accessed so without the physical cable. So weak wireless security can allow unauthorized users to try to connect. So just to address this, I added one wireless access point and one wireless laptop, which is here, to both Sydney and Melbourne. So Sydney uses the SSID ABC SID, this one, ABC Mel. Yep, this one, and this one, this one. So the wireless laptops were tested and were able to communicate with the both local remote networks. So for a real network, I can recommend the WAP2 Enterprise or the WPA3 Enterprise with 802.1x and the radio server. This one is just for demonstration. That's why we use the WPA2. So this allows the individual user authentication instead of giving all employees one shared network. So I would also separate staff and guest wireless users into different virtual LANs. Next, so the next problem is network monitoring. Yeah, the concern is network monitoring. So the company needs a way to identify the problems with the routers, switches, servers, and network connections before they seriously affect the users. So for this problem, I can recommend this Savix. So Savix is a open source network monitoring system. It can monitor routers, switches, servers using tools such as SNMP. It can also provide alerts, dashboards, graphs, and historical monitoring information. So next is branch-to-branch communication. So The final problem or requirement is the communication between the Sydney and Melbourne. So the company requests a point-to-point GREPP antenna between these two branch routers. So just to address this problem, I created a GRE tunnel between the Sydney and Melbourne routers. GRE creates a logical point-to-point connection over the existing WAN network. So before demonstrating the tunnel, I will restore the static routes that send the branch traffic to the GRE. So I already restored the static routes here so that the Sydney and Melbourne networks will now use the GRE tunnel. So I will show you guys the status of the GRE here. Yep, so here we can see the tunnel 0. Um, it uses the IP 172.16.0.1. So both the status and protocol are up, and this shows that the GRE tunnel interface is operational. So next, we will test the GRE endpoint. Yep, so I test the communication between the Melbourne GRE endpoint at 172.60.0.0.2. So the ping is successful, and this confirms that the two tunnel endpoints can communicate. So I will prove the traffic using the GRE now. So we will go back here. So the routing table now shows Melbourne IT and HR network uses the 170.16.0.2 as the next hub. So I will now the trace route confirms the path as well. So the first hub is 170.16.02, which is in here, and which is the GRE tunnel address of the Melbourne router. So the next hub is the Melbourne IT computer, which is in here. Just this confirms that the traffic from Sydney to Melbourne is passing through the GRE tunnel. So we'll go for security limitation of the GRE. So the one important point about GRE is that GRE itself does not encrypt the data. It provides the encapsulation and creates a logical tunnel, but it does not provide encryption by itself. So for a real company connection over the public internet, I will recommend combining the GRE with IPsec. IPsec will provide encryption authentication for the communication and between those two branches. So that's all. Thank you.